Now we want to switch gears and talk about vascular networks that is used to deliver healing agents to a composite. First, let's see why people started to think about vascular networks. Obviously, one reason is that you could have been inspired. They could have been inspired by the veins in our body. That blood is circulating, and blood carries a lot of healing agents that can cure our wounds, the injuries. However, along the same lines, basically, the thought was that if I have microcapsules, and if there's a crack somewhere and it breaks, fine, I can deliver some amount of healing agent wherever the damage is locally. Everything in microcapsules is local. When microcapsules fail here and crack goes here, this amount will be released in the vicinity of the crack and inside the crack. The amount of the material that will be released is limited. It's equivalent is equal to the internal volume of the microcapsules that are broken. And so then one approach to address that is to put holes in the composite that can be accessed from outside the composite. An example is something like this, in 1 dimension, in 2 dimensions, or in 3 dimensions. Obviously, the more dimensionality you add to it, the more complicated the fabrication becomes. Now, if there is a crack somewhere in the sky, so for instance, if the composite starts to break right here, it will inevitably damage some of these tubes, and whatever liquid is inside can be delivered to this place. Now, because these are extended in one direction, the amount of material that is inside them is much more than individual microcapsules, plus you can supply more from these exit points here. Again, these are in 2 different colors because typically we're assuming that there's a reaction that requires 2 components, and so it requires 2 parts. One thing I want to, so now typically they can be put, the way these structures are made, they can be divided into 2 broad categories. Arguably, one of the categories by itself can be split into 2 categories. Okay, so now the first one is where you literally put tubes inside your composite. This is exactly the way our sewer system works. You know, you put tubes in the ground and liquid transfers through that. So basically, there is a boundary that is solid that separates the hollow core from everything around it. Now, another category is through sacrificial material or fugitive networks. Basically, both are the same, but in terms processing is different, but in many ways, both are the same. And so the idea there is that, let's say, as an example, I put a fiber inside my composite. So initially, the fiber is filling a volume inside the composite. But then I do something, for instance, through thermal treatment, I get rid of the fiber itself after the composite is cured. Initially, composite is liquid. I put the fiber in, I cure everything, then I get rid of that fiber. And so in place of the fiber, now there's a hole. The boundary is the matrix itself that now has solidified. These fibers are different from carbon fibers or glass fibers that are used for reinforcement. These are sacrificial fibers, just an example. Now, I want to bring your attention to, let's say, a building block here of this composite. You see these little white things, white circles. Okay, there are many, many here or here or here. These are individual fibers. In this case, I think they were glass fibers. These are reinforcement fibers, okay? And you see then a large opening, which is here. So basically, you see a large opening, which is, I'm showing it with the star, or there's another one here. One problem with these microvascular networks that you will see often over and over and over again is that the diameter of these microvascular networks is in the order of tens of microns, sometimes hundreds of microns. Now, the diameter of a glass fiber is how much? Or a carbon fiber is how much? About 5 microns. So 12 times smaller than the diameter of a hole, which means, or diameter of the tube, which means in order to put one of those glass fibers, I have to remove 120, 140 or something, or 150 of these load-bearing fibers. And so, which means I have two choices. Either I put them like this much far away from each other, which is relatively large if you think about it. The ply thickness of a composite is in the order of 100 to 150 microns. These are 200-300 microns apart from each other. So I have two choices. Either I put them so far away, or if I put one tube here and I put another tube here, so that I can handle cracks that even go like this, I make it more likely for cracks to hit one of my tubes. In that case, I have to remove a lot of the fibers, load-bearing fibers. So, so some trade-offs exist here. Either I put these large tubes very close to each other so that I can handle, I can stop and heal cracks with high likelihood, so that cracks can hit them with higher likelihood. In which case I have to remove a lot of fibers, load-bearing fibers, or I put the tubes or holes very far from each other. That lowers my ability to stop and heal cracks, but at the same time, it doesn't reduce my properties of the healed material, I'm sorry, virgin material. It doesn't compromise the properties of the virgin material. At this point, if I explained everything properly to you, you should be asking yourselves, okay, so what? Just reduce this diameter. Make this, instead of, make this guy, instead of 60 microns, make it 10 microns. Put, instead of having 160 micron here, or 160 micron here, and 160 micron far away here, turn them into 5 micron tubes and put them closer, distribute them closer to each other. And to that, I would say, I wish we could, but there's a problem there. We are limited by the physics of the problem. From fluid dynamics, we know that the pressure, this is Poiseuille's law. It describes the flow of the laminar flow of a fluid inside, of a Newtonian fluid inside a tube, and it relates pressure drop. So let me tell you what each is. This is pressure drop along a length L of the tube. This is viscosity, this is the diameter, and this is the flow. So basically what it is explaining is, if I have a tube like this and I pass a flow Q through it, because of this flow, and let's say this length is L, I will have a pressure drop delta P, which means for this flow to pass through this guy, I need, whatever the flow on the far end is, I need to add this much flow to the beginning of the tube. Now, the problem is this guy. Oops. The problem is basically this guy, d to the power of 4. So if I go from 60 microns to 6 microns, comparable to the diameter of an individual carbon fiber, I have to increase the pressure by 10 to the power of 4 times. And that's a dangerous proposition by itself, because solids in high pressure is not necessarily a good thing. You may start damaging your composite before you heal it, damage it more before you heal it. And so here, or you may say, okay, I'm going to reduce Q as well. But if you reduce Q, again, you're reducing your healing capacity. So with all these considerations, the field has converged on diameters of this order of magnitude. Now, there's some that is 200, 300. These are some that are 50, 60, but it's about the same range, about this range. Now I'm going to explain each of these three in the subsequent. I'm going to explain. I'm going to explain these two and three in the next video. And I'm in the next slide, in the next video, I'm going to start with this, and then I will explain these two.